This is STEM in 30.
Just like a planet. Wouldn't it be cool to go to space?
Hey, I think I heard you guys talk about wanting to go to space.
Yeah.
Do you know the museum has an exoplanet travel agency?
No.
Well, if you go that way, you'll find the office. And here's some brochures for you to take a look at on your way.
Thank you.
Wow.
Hello and welcome to the Exoplanet Travel Agency. We are here to help you book the perfect vacation anywhere in the galaxy. Where would you like to go?
What about this one? Does this cloud sparkle?
Cancri 55? Oh yes, those clouds sparkle like diamonds in the sky.
But just so you know, it's 41 light years away and you'd better pack your fire retardant suits because it's covered in lava.
Huh?
Yes, it's covered in lava and 41 light years away. This is not a quick 239,000 mile trip to the moon. We're talking light years here. Do you all know what light years are?
No.
Don't worry, we are here to help you out. We're going to send you over to the Interstellar Distance Division to learn a little bit more.
Welcome to the Interstellar Distance Division. I'm Barb, and I understand you guys want to learn about light speed.
Yes.
So we're going to pretend that my laser pointer is going to go to Mars. So we're going to point my laser pointer at Mars. Ready? Don't worry, I'll tell you when it gets there. So let's talk about light speed. It's pretty fast. In a vacuum, light travels at 186,000 miles per second. Pretty fast, right? You guys look pretty fast. Let's see if you can beat it in a race. So Bella, I want you to take this and take a few steps down that direction. I'm gonna aim at that board. All right, let's line up. That light still hasn't gotten to Mars yet, so you got a chance. On your mark. Set. Oh, nice try. So let's talk about light years. A light year is the distance that light will travel in about a year. All right, let's take a look at this marble. Let's pretend it's our solar system all the way out to Neptune. The closest exoplanet is Proxima Centauri b. It orbits the closest star, which is Proxima Centauri. It's over 4 light years away from us. How far away do you think that is?
Probably over here.
It's a good guess, but it's a little further away. Let's take a walk. All right, so with our marble the size of our solar system, the closest exoplanet was way over here, about 90 meters away, about the size of an average football field. So now you understand the distance of a light year and light speed. So now you can book your travel.
Ah, you're back. What would you like to look at now?
This planet looks like Tatooine from Star Wars. It has 2 suns.
Oh, that's Kepler 16b. Good choice. It's where your shadow has a friend. 2 stars.
How do you find this stuff?
Look, I don't find exoplanets. I just book travel to them. If you want to learn more, we'll send you over to the Planetary Detection Office and they'll help you out.
But you better take some sunscreen.
Actually, double up, Buttercup.
It's nice there, but I'd only give it 2 stars.
By the way, that light just got to Mars.
Hi, welcome to the Planetary Detection Office. I'm Shauna. I hear you all want to learn something about how we find exoplanets. Great. Well, I'm going to show you using this model. Now, if one of you can hit that switch to start our planets. Stars, like this light bulb, make light and they shine it in all directions. But if you can see the little planets around it here, the planets aren't making their own light. They're just reflecting the light that the star shines on them. If this is a star somewhere in the sky, if I point a telescope at that star and I'm looking for these little exoplanets, can I see the planets? Most of the time, no, right? They're too faint, they're too small, they get lost in the light of their star. So we can't see the exoplanets directly, but we can figure out that they're there using something that we can see, which is the star's light. Now that's what this is doing. This is a light sensor. It's looking at that light bulb star and it's measuring how much light it sees. I'm gonna start the measurement. So on this screen, this is how much light our light sensor is seeing. Now what is happening to the brightness of that star? It's shifting. So what is causing the light to drop, or it to look like the star is getting less bright?
Planets blocking it?
Exactly. Every time one of those little exoplanets goes in front of the star, it blocks a little bit of the light, just like you might do with your hand blocking the sun. If we can't see this part in our telescope, if all we get is the measure of that brightness, we can still figure out a lot about those exoplanets. So just from this, we can tell how big the planet is. What is it on the graph that tells you how big the planet is?
How long the dip is?
Exactly, how much light it blocks. A bigger planet is going to block more light. It's going to make a big change in the star's brightness. A smaller planet is only going to block a little bit of light. What's really amazing is that the telescopes that do this work, that measure star brightness to find planets, they're measuring really tiny changes. A planet the size of Jupiter around a star like the Sun would make a change of about 1%. And that doesn't sound like much, but that's pretty easy to measure. That would be the equivalent of having an 80-story skyscraper, a huge building, all the windows have light coming out of them. 1/10,000% change would be like somebody going to one window and lowering the blinds 2 centimeters. It's really tiny, but we have instruments like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite that are looking at stars, measuring these changes and finding exoplanets. So if you're going to an exoplanet, you want to know how big it is, you want to know how much gravity there will be, are you going to feel really heavy, or are you going to be able to bounce like they did on the moon? You can also figure out what the temperature is going to be like, because you need to know what to pack. And we can do that by looking at how long it takes between the dips. That dip represents one transit. A transit is when the planet passes in front of its star. It's like a tiny eclipse. From one transit to the next, that's 1 year. That's one orbit of the planet. So if we look at the time between transits, that tells us how long the planet's year is. And from that, we can calculate how far away it is. Because you may have noticed the closest planet is moving the fastest, and the farthest planet is moving the slowest. It has to do that to be gravitationally stable. So if we calculate how far away that exoplanet is from its star, we can figure out, is it really close? Is it going to be really hot? Is it farther away? Is it going to be cold? If you're going to visit an exoplanet, you probably want to find one that's just the right distance to be warm and comfortable. Y'all feel like you're ready to find some exoplanets?
Yeah.
Excellent. All right, why don't you head back to the office and book your vacation?
You know what's going to make our lives miserable?
What's that?
when the Super Puff brochures come out.
Oh, the exoplanet gas giants, the size of Jupiter with a density of their atmosphere of cotton candy?
Yep, everyone wants to go to the cotton candy planet.
Oh, welcome back.
We learned about finding exoplanets.
Did you learn how telescopes on Earth are used?
Earth telescopes?
Yep, telescopes right here on Earth.
All right, you guys got to learn a little bit more. Put on your video viewers.
Hi, my name is Carly Solis. I am at George Mason University. I actually graduated from here with a bachelor's in physics and astronomy. I also volunteer at the National Air and Space Museum. We are here to talk to professors and students about exoplanets.
My group's discovered over a dozen exoplanets orbiting other stars over the past 5 years, and it's been a really exciting time. I am an exoplanet astronomer and I do observational astronomy, so what I try to do is I look at other nearby stars to find evidence for planets around them. And so I use telescopes around the world and in space to do that. There are a lot of advantages to using telescopes on the ground that you just can't do in space because of costs. You can have bigger telescopes on the ground and you can collect more light so you can see fainter things and gather more signals. With telescopes in space, you can measure things much more precisely than you can from the ground because the Earth's atmosphere isn't in the way.
I specifically study how our atmosphere affects the spectra that we look at when we're looking at transiting exoplanet, which you learned about before. When we're using a ground-based telescope and the spectra comes in through our atmosphere, the atmosphere interacts with that light and messes it up a little bit. So then when we're trying to see the red or blue shift, how far away or towards us the star is moving, it's a little bit messed up. So our readings have some error in them. So my research is helping others know how much error might be in their measurements. So since mine is completely simulated, I know every single component. So I can isolate exactly what the atmosphere is doing just to the spectra.
I specifically do research studying M-dwarf type stars. So an M-dwarf star are the most abundant stars that we have in our universe. They're the most common. And they're also the coolest, the dimmest, and the smallest. When we look up at night, even though they're the most abundant, we don't actually see any of them with our naked eye. It's actually a really good thing when we're looking for exoplanets because since they're so dim, when an exoplanet transits in front of that star, it's going to block a lot more of its total light, making it a lot easier to see if there's an exoplanet.
3, 2, 1, 0.
NASA launched the test mission, the Transiting Exoplanet Survey Satellite in 2017, and it's been surveying the entire sky in 27-day chunks over the course of 2 years, both the southern part of the sky and the northern part of the sky, which is hard to do from the ground. You know, in space, you don't have the Earth in the way to see the whole sky. And it's been making tremendous number of discoveries. Over 1,000 candidate planets have been discovered with that mission so far. And you can't do the science without the people to analyze that data. Those things go hand in hand. So we might get data from a telescope in the form of a digital image, but that's just it. You can look at it, but what do you got to learn from it? And to learn from that, you need people to interpret that data.
My project basically is validating test exoplanet candidate. That's test with transiting exoplanet survey satellite. And my role is to confirm or reject the detection made by test that satellite on the exoplanet. And we do that follow-up with our on-campus telescope, which is 0.8 meter reflecting telescope.
Now we're at the George Mason University Observatory with Dr. Harold Geller.
I'm the observatory director here at George Mason University, and welcome to our observatory.
How do we do observing here with such a big city right next door?
You have the advantage of modern day electronics. It allows us to amplify signals of light coming from distant space. You also have the ability to focus in on specific frequencies of light so that the light from the city lights are diminished, and you also have the light gathering power of a 32-inch diameter mirror, which allows you to increase the intensity of the light that's available to you. This type of telescope cannot be used during the day. You don't want it to get anywhere near sunlight because of its light intensification capabilities. It would literally melt the mirrors that are used to focus the light. So this is only used at light, and you're looking at dim objects that are up there in the sky.
Thanks so much for showing us around.
My pleasure.
At the top, you saw some exoplanet art.
Would you like to know how to make your own?
Yeah.
Pop those video visors back on and take a look.
Art is for everyone, and the only limit is your own imagination. This especially goes for exoplanet art. We can't see these faraway planets in great detail, so we have to use our imagination when considering what they might look like. The authors of the book Exoplanets explain that there are a lot of exoplanets, and there is no wrong way to imagine what they may be like.
The astronomy community is discovering planets outside of our solar system at the rate of about 1 per day. And if you use that rate and see how many planets are around our nearby stars, we suspect that there are more planets in the observable universe than the combined number of heartbeats of all the people that have ever lived on Earth.
We figure that if you can imagine any exoplanet, provided it doesn't violate some law of physics, it probably exists somewhere.
You can create your own exoplanet art using some simple materials. Start with a poster board and just a few colors of spray paint. First, put down the colors of your primary planet, usually 2 or 3 colors, and think about shadows and where the light is coming from. After layering your spray paint, take a plastic bag and lay it over, and pull it up. This creates the planet look. Now cover your planet and paint your sky black. Next, flick white paint over the painting to represent stars. Use a straight edge to spray straight lines. Uncover your planet and voila! An exoplanet! You can always learn additional techniques like comets, foregrounds, and rings.
Exoplanets are not the only inspiration for space art. The Juno mission to Jupiter has inspired some amazing pieces. Scott Bolton, the principal investigator, discusses how science influences art and how art influences science.
And I really believe there's an intersection of art and science which is very important to us all in almost all fields. And here you see a lot of the images, and this is one of them, where somebody posts something that they're inspired in some artistic fashion. There's science in this too. They're taking the swirls and they're showing you in a new way, and that is exactly how science works too. Is I look at a picture from a different way and I all of a sudden see some feature that I wouldn't have otherwise recognized. That's the idea of the original stretch of colors. Mm-hmm. This is more extreme. I'm not sure scientists would do what a lot of the amateurs are doing, but they are going to start now because we're learning so much from it. But it's also just a beautiful picture.
No matter what your medium or your inspiration, you too can be an exoplanet artist.
Paint, pencils, Photoshop, or even pancake batter can be the way that you share your imagination with the world.
What far out places will you dream up? What art will you make?
How's your lunch?
It's too cold.
Ah, mine is too hot.
I hate it when they can't get it just right.
Pretty cool video, wasn't it?
You're trying to give us trips to places we can't actually go.
Oh, those are great places to visit, but you wouldn't or couldn't really live there.
Look, if you want to sustain life, you have to be in the Goldilocks Zone.
Yeah, like Proxima Centauri b. It's 4.2 light years from Earth and it falls into that Goldilocks zone.
Okay, I'll ask. What's a Goldilocks zone?
Look, I don't define Goldilocks zones. I just book travel to them.
But before you go there, you're going to need to learn a little bit more about them.
And you're going to need these.
We've all heard the story of Goldilocks and the 3 bears. But what does that story have to do with finding exoplanets that could sustain life? To find out, let's take a look at our very nice Solar system. Once upon a time, there was a solar system. At the center is the sun. Orbiting around the stars are 3 bears. Let's put our bears into place. First, there's Papa Bear, who's closest to the sun. They're holding Mercury. Next is Mama Bear, holding Jupiter. Then there's Baby Bear, who has Earth right in the middle. Now let's bring in Goldilocks. Their first stop is Mercury with Papa Bear. Ooh, that's way too hot. Can't stay here. Goldilocks skips along to Jupiter with Mama Bear, but it's way too cold. Let's see where Goldilocks can go next. Next stop is Earth and Baby Bear. Ah, that's just right. The Goldilocks Zone in a solar system is just right for planets to sustain life. But this zone can change depending on the size and temperature of the star in the center. For instance, if the star is a very hot blue giant, then the Goldilocks Zone would have to move farther out from where Baby Bear is right now. But if the star were a cooler burning red dwarf, then Baby Bear Earth would have to move closer to sustain life. When searching for the Goldilocks Zone, scientists look at both the planets and their stars. Once they find a planet that's just the right distance from its star, they know that planet is in the Goldilocks Zone and could maybe sustain life. The end.
Okay, you've booked some terrible vacations for us. Double suns, lava, light years.
Don't forget about cotton candy planets, planets being devoured by their own sun, red sky planets.
Don't you have any good vacations?
Sure, let's run your data through the interplanetary vacation machine and we will see what your perfect destination is. Carry the 4. There it is.
Oh, there you go. Your perfect planetary destination. Put on your visors. We will send your perfect vacation to you.
Take a look. I think you're gonna like it.
Wow.
Your perfect planetary destination is the 5th largest planet in its solar system. Smaller than the 4 gas giants, but larger than the 3 other rocky planets it hangs out with. Its orbit keeps it at almost 93 million miles from its middle-aged star, putting it in a perfect Goldilocks zone. Its atmosphere is roughly 78% nitrogen and 21% oxygen, with trace amounts of water, argon, carbon dioxide, and some other gases. 70% of the planet is covered in water, but there's enough solid crust for tourists to travel on. This planet is roughly 4.6 billion years old. Most importantly, this planet is known to be able to sustain life found in its deepest waters, all the way up to its highest mountains. Your perfect planetary destination is Planet Earth!
Earth? We're already on Earth.
Yeah, Earth. Earth is awesome.
Not to mention that it is the only planet that we know of that can sustain life. There is no planet B, so we need to take care of this one.
We're kids. What can we do?
Oh, there is plenty that you can do. Pop those video visors back on to see how you can keep our planet nice.
There are many simple things that you can do to help keep our planet in good shape. Turn it off. Done watching TV? Turn it off. In fact, if it's not in use, then turn it off. If you're leaving a room, turn the light off. Brushing your teeth? Turn the water off when you aren't using it. Plant a tree. Think about how many trees there would be if everyone planted a tree on their birthday. Ditch the plastics. Get a reusable water bottle. One-time use water bottles fill up landfills. Don't pack your lunch in plastic baggies. Use reusable containers. And take reusable bags when you go shopping. Don't litter. Put your trash in trash cans, recyclables in the recycle bins, and where possible, compost food waste. The worms love our food waste. This helps keep waste out of our waterways. Go outside and play. Enjoy our wonderful world. Just by doing these small things, you can make a large impact.
Earth is pretty great.
Earth is pretty great, but just because you're on the perfect planet doesn't mean that you shouldn't be looking for other weird worlds.
And remember, never give up, never surrender, and never stop exploring.